Hi students, welcome to Random Variables and Stochastic Process series lectures. So now in this video, I would like to explain about probability density function. In the previous videos, we have seen what is random variable, what are different types of random variables, what are the conditions for a function to be a random variable, and distribution function properties, and now probability density function. So if I have the random variable x, and its corresponding density function is given by fx of x, and this is given as the derivative of the distribution function for minus infinity less than x less than infinity. So this is simple definition of the density function. A density function of a random variable is simply differential of its distribution function. Okay, now if I'm taking the distribution function as a discrete on this discrete distribution function, then for discrete fx of x, the density function is given by fx of x is equal to d by dx of fx of x, and that is given by dy dx of, and sigma n is equal to 1 to infinity, or you can take, instead of taking n, you can take I. So probability of xi u of x minus xi. So this is the definition what we discussed already for distribution function. So for discrete random variable, we have this equation here. Probability of xi d by dx of u of x minus xi. So probability doesn't change, the value doesn't change. So you need to take differential of the step function. So as per signals based on knowledge, you can take differential of the step signal gives you an impulse signal which is represented as like this, del of x minus xi. So this is the density function expression when the given distribution function is a discrete one. And already you know that the impulse function is given by del of x is equal to 1 at x is equal to 0 and 0 for others or for other values. So this is, you should know. Okay, so this is the basic definition point of the probability density function. Let us discuss about properties of the probability density function. So now properties, and the first property is 0 less than or equal to fx of x for all values of x. So that means sorry, the density function is not a negative one, so it's a non-negative function. And the second one is integral minus infinity to plus infinity fx of x dx is equal to 1. So from this I can explain the property with respect to one graphical representation. So the function with respect to this one is going to be taken like this, and on the y-axis you can take the density function of x of x, on the x-axis you can take x value. Okay, so it is given in the range of minus infinity to plus infinity, so I can take the limits here. So the total area under this curve from minus infinity to plus infinity is taken as unity as per this property. And the third property, fx of x is equal to integral minus infinity to x fx of x dx. So this is going to indicate that from this graph, I'm going to explain again. So here the limits are given from minus infinity to up to one particular value that is going to be taken as x, a positive value they given. Okay. So here the value is given up to x only. So the area under this limits minus infinity to x will gives you corresponding distribution function of that particular random variable by using the density function of x of x. And the fourth one, probability of x1 less than x less than or equal to x2 will gives you integral x1 to x2 fx of x dx. So that is again with respect to figure, I can write this one. So here the given limits are only positive values. So I can take this one as x1 and this one as x2, and the area under this curve from the limits x1 to x2 will gives the required probability of x1 less than x less than or equal to x2. So this is the fourth property, and from the definition of the probability density function, the distribution function, we have the expression for this property x1 less than x less than or equal to x2 as fx of x2 minus fx of x1. So which is taken as integral minus infinity to plus, sorry, integral x1 to x2 fx of x dx. So these are the properties of the probability density function.